challenge. Span. So the idea was you could just say number 1, it's a subspace. Any span is a subspace. But not everybody recognized that was a span. You could go through the 3 properties to verify, and that works, but it was kind of tedious to go through the properties. The second one, that polynomial thing on the first page, all 3 of the 3 properties you check for subspace fail. So then I was hoping, well, no matter which one they try first, they'll find out it doesn't work. But then some people were saying all 3 were verified. And I'm like, no, 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 all 3 fail. A polynomial is no more than its coefficients. So just when you write something like P of t equals, what was that, a plus t squared, right? That's no different from a plus 0t plus 1t squared. And it really, all it is the coefficients, a, 0, 1. The t has nothing to do with it. The t is just sort of a placeholder that keeps the coefficients separated from each other. So this polynomial, as far as a vector space element, is just like that vector a0, 0, 1. And because of that 1 in the third position, it's impossible to have 0, 0, 0. So, okay, we'll come back to that before the final, but that's really all I want to say about the test. So we got to start talking about 5.1 today. And before I forget, next Monday, there is no school, right? We have a day off on Monday, so it's a short week. Next week, Monday is a holiday. And all right, so what holiday is it? It's called Veterans Day. I mean, you know where that day comes from? November 11th. The day the World War I, what we call World War I, some people call the Great War of Europe, was the armistice was signed on November 11th at the 11th hour, but it wasn't 1911. It was 1918, I want to say. I think 1918. And it's evolved into what we call Veterans Day. And what's up? Extras, so if you need a 5.1, let me see. I think you should all have it, because I only have a couple left, but I do have a few left. Victor, Amelia.
Thank you.
Okay, so please just, if you get your test at the end, if you just came in, because we're going to start now. All right, so Chapter 5, A Whole New World, we're starting here. And first thing the title of this section is called Eigenvalues and Eigenvectors. Eigen is a German word, and so you pronounce it with kind of a German accent instead of Egen. You don't sound like you're hip if you say Egen, so say eigenvalues. And value. So it's not like the word really tells you that much about what a eigenvector is. We're going to have to experience them and work with them to get a better feel. All matrices are square in Chapter 5. So Chapter 5 is square matrices only. And think of, what are the kinds of topics that involve only square matrices that would never be m by n? Inverse only has to do with square matrices. Determinant And now we're going to, eigenvalues, we're going to add to that list. Only has to do with square matrices. And, all right, so let's start doing some problems here. So let A be a square matrix. A vector x in Rn is called an eigenvector of A if x is different from 0. Eigenvector can never be 0, never, ever, ever. If ax equals lambda x for some scalar lambda. That's a Greek letter, lambda. It looks like this, and it's spelled that way. And it's just, I don't know why we use that letter for eigenvector, but we do. It's, oh, I guess I also have it on the handout. So what is this saying? When you say ax equals lambda x, now we're used to thinking of a linear matrix multiplication as representing a linear transformation that takes x to ax, right? We've talked about that quite a bit. And if a is square, we're going from Rn to Rn. And so let's see, let's put a little x in our picture and maybe a ax over here in the image space. When the domain and the codomain are the same, a lot of times we just imagine one copy of Rn. And instead of imagining a vector in the domain corresponding to its image in the codomain, we kind of have this idea that we change the vector the vector x into ax, all sitting within Rn. That's where the idea of transformation comes from. When we use that word transformation, it's like the vector. It's just a visual thing. There's no reason why you can't think of it this way, but when the domain, codomain are the same, often we imagine that picture just sitting in one copy of Rn, which all my Rn's seem to look an awful lot like R3, right? I think there's a nice 3 blue, 1 brown video out there on the internet that illustrates some of the geometry of eigenvectors and eigenvalues, so you might want to take a look at that. But the one thing I would say is if this is true, what is that actually saying geometrically? So let's take this picture away. Let's just imagine that one copy of Rn where we're starting out with some vector x. If a times x is lambda times x, that's saying that the image of x is some scalar multiple of x. And so geometrically, we're either just stretching that vector out along the same line, the line that it's on, or we're possibly pointing in the opposite direction. It could be a negative scalar multiple. So normally, a linear transformation moves a vector around, changes its direction, changes its shape. But if it doesn't change the direction, if all it does is scale the vector, then that vector, that scaling factor is called an eigenvalue, and that vector is called an eigenvector. Okay, let's start doing some problems. So they are paired together, right? Lambda is called the eigenvalue. X is called the eigenvector that corresponds to the eigenvalue. And we're going to jump back and forth between eigenvalues, corresponding eigenvectors, eigenvectors, and their corresponding eigenvalues as we go along. So for any vector v in Rn, AV is some other vector, often very different from v. But if AV happens to be a scalar multiple of v, then v is called eigenvector. So that if my pictures on the side didn't help much, that statement is something you want to contemplate a little bit. And so let's just do couple problems here just to get warmed up. So in the exercise, let A be this matrix. Is 2, 1 an eigenvector of A? And so doesn't have a number. So in part A, what are we going to do? We're just going to take that matrix 1, 4, 2, negative 1, and multiply by that vector 2, 1, and see what happens. Okay. So let's see, what do I get? I get 6 in the first entry, right, and 3. And so the question we're asking ourselves is 6, 3 a scalar multiple of the vector 2, 1? And that shouldn't be hard to see here. The answer is yes. Right? 6, 3 is equal to 3 times 2, 1. So 2, 1 is an eigenvector. Okay, so that's the simplest way you can understand what an eigenvector is. I multiply by the matrix, and the result that I get is a scalar multiple of the column vector that I started out with. The corresponding eigenvalue here is 3. Corresponding eigenvalue. B. So let's take that same matrix A, 1, 4, 2, negative 1, and multiply by 3, 1, see what happens. Let's see, I think I get 7. And then 6 minus 1 is 5. Can you see that 7, 5 is not a scalar multiple of 3, 1? Because to get from 1 to 5, I would have to multiply by 5. But if I multiply 3 by 5, I get 15 and not 7. So 3, 1 is not an eigenvector. So the linear transformation involved here is doing something different other than just scaling the vector 3, 1 when it gets applied. All right, so now let's take this a little further. Let's actually show that 6 is an eigenvalue of this matrix. So sometimes you start out with eigenvector first. Sometimes we're going to start out with eigenvalue first and find the corresponding eigenvectors. So we're going to move on. And I think I need a little bit of room, so I'm going to turn off the projector, and I'll just write that problem on the board. If I were you right now, I would just be sitting there thinking, like, why would anybody care about this? Like, it would seem really mysterious to me that this might be something important. So you should feel that way. So we're going to show that 6 is an eigenvalue of the matrix A, which is 3, 12, 1, 2. So what we have to do, we have to find a non-zero vector x such that ax is equal to 6x. Okay. That's what it would mean. Say non-zero all the time. I mean, 0 interesting, not relevant here. We got to find a non-zero vector. So we're going to try to solve for x. Take this equation and solve for x. And to do that, we're going to do something we've done before, I think, in here. Get one side equal to 0. Ax minus 6x equals the 0 vector. So we're going to turn this into a homogeneous equation. And to do that, I want to factor out an x. And to factor out an x, I have to rewrite this equation in the following way. Minus 6i x equals 0. I can replace the 6 with 6 times the identity matrix. Then I can write this as a minus 6i in parentheses times x equals 0. But before we plunge ahead, I want to talk a little bit about that 6x and 6ix business, just so you understand that notation. X has just 2 components here, right? So 6x is just 6x1, 6x2, right? I here is the 2 by 2 identity matrix. The same would be true for any dimension. We would just have I3 or I4 or I whatever. 6i, when you take a matrix times a scalar, we multiply each entry by that scalar. And the zeros won't change, but the ones will. So it ends up looking like that. So notice that 6ix, if I multiply those, 6, 0, 0, 6 times x1, x2. I just need to verify this myself. I wouldn't be convinced without writing it out. That this is going to come out, these two are going to be the same. So multiplying a scalar times the vector x, multiplying each entry by 6, is the same thing as multiplying 6 times the identity matrix times that vector x, right? Because if we go, what do we get? We get 6x1. And my second entry is going to be 6x2. So just notice these are the same. Okay, so that was just an aside. To kind of make sure we weren't freaking out about the notation. So that red is just an explanation of why I can replace 6 with 6i here. See, I can't take a matrix minus a scalar by itself. I need a matrix minus a matrix to be able to do this factorization. And so take that step there. I'm just going to recopy it over here. A minus 6i x equals 0. We're just going to solve this homogeneous equation. Solve this homogeneous matrix equation. which you've done a million times now, and so you're like, ugh, again. What is a minus 6I is 3, 12, 1, 2, minus 6, 0, 0, 6. So that's going to be a different matrix, right, from A. Now things change a little bit. Watch me, because this is where I always mess things up. 1, negative 4. So I could set up an augmented matrix for the homogeneous system. Negative 3, 12, 1, negative 4, 0, 0. And I want to solve that system. I could interchange. Leave that 1, negative 4 up above, and then I could add 3 times the first to the second, right? So negative 12 plus 12 is 0, 0. And I guess that's in reduced form, so I have x1 minus 4x2 equals 0. x2 is free. So my solution, x is going to be 4x2 x2, or x2 times 4, 1, where x2 is any real number. So we've actually found infinitely many eigenvectors. So we have actually found infinitely many possible eigenvectors corresponding to the eigenvalue. All right, lambda equals 6. We want to get used to, didn't have a parenthesis here. Using that lambda to denote eigenvalues. For example, if x2 equals 1, we get 4, 1 is an eigenvector. If x2 is equal to negative 3, negative 12, negative 3 is also an eigenvector. So I think you can see that because we obtain these eigenvectors by solving a homogeneous system, we tend to get this vector subspace of solutions. We're going to tend to get infinitely many. But note, x2 equals 0 does not give us an eigenvector. So there's one value of x2 that can't be used to give us an eigenvector, because x2 equals 0 would give us 0, 0. And the 0 vector is not an eigenvector, is never an eigenvector. So I gave you a teeny tiny little spot on the handout to write all that stuff. Now we're going to turn the page. Yeah, I'll put the projector back on for a moment. so second page. So if this lambda, so lambda is some number, some scalar, some real number. If lambda is an eigenvalue of A, then the set of all vectors x for which this equation is true, that's the kind of equation we just solved with lambda equals 6. So the set of all vectors for which this is 0 is the null space of a linear transformation, is therefore a subspace of Rn. So in this example, the subspace that we got was subspace of dimension 1, where we had a basis of just one vector, 4, 1. So that subspace is called the eigenspace of lambda. The eigenspace is full of all the eigenvectors that correspond to that particular eigenvalue. Could be two-dimensional, could be higher dimensional for a higher value of n. To me, it's a little bit weird, though, because 0 is in the eigenspace, okay? Because to be a subspace, you have to have 0 included, the 0 vector. But 0 is not an eigenvector. So the eigenspace is always allowed to have, an eigenspace is always allowed to have one vector that is not an eigenvector, the 0 vector. All the other vectors in the eigenspace corresponding to a particular eigenvalue are eigenvectors. And also, I think it's worth noting that if the only solution to that homogeneous equation is x equals 0, so if there's only the trivial solution, then lambda is not an eigenvalue. So there aren't that many numbers we're going to see where you actually get non-trivial solutions. So there's going to be a very limited number of eigenvalues for a particular matrix. Felix?
Is A always a linear transformation?
Yes. I mean, so...
it's the matrix of a linear transformation.
Yeah. So the linear transformation I'm referring to here isn't just A, it's the A minus lambda I linear transformation. So in the example we just did, this is the matrix of the linear transformation. The null space of the linear transformation represented by this matrix is a one-dimensional subspace spanned by that one vector, right? Just like you found a basis for the null space on our last test.
If I need to check that matrix, it comes from a linear transformation or not in a general process.
For us, we think of any n by m matrix as being the matrix of a linear transformation. We do not have matrices that are not matrices of linear transformations. All right, so what we got to do now is take a matrix. Here's a 3 by 3A. I'm telling you lambda equals 2 as an eigenvalue, and I want you to find a basis for the corresponding eigenspace. And it's really just like what we did here. I think maybe I can leave the projector on and do the work on this side. So on this exercise now, I'm giving you a particular value for the eigenvector, right? So we need, I'll write down A first, 0, 0, negative 2, 1, 2, 1, 1, 0, 3, right? Well, here we're interested in A minus 2I, 0, negative 2, 1, 2, 1, 1, 0, 3. Because I'm in dimension 3 here, where n is 3, I is the three-dimensional identity vector, so it's going to be 2, 0, 0, 0, 2, 0, 0, 0, 2. There's my 2I. And so what do I get? I get negative 2, 0, negative 2, 1, 0, 1, 1, 0, 3 minus 2 is 1, I believe. Okay. So we want to solve the matrix equation 2, 0, negative 2, 1, 0, 1, 1, 0, 1. Well, let's just say x equals 0. And I think I'm being particularly nice to myself because, well, let me just write down augmented matrix. So I'm not doing anything yet. I'm just going to recopy. And row reduce. And this one goes really, really fast. I get 1, 0, 1, 0, and 2 rows of zeros. So I have x1 plus x3 equals 0. X2 and x3 are free, right? So I have only one pivot position, and corresponding to x1. So x2 and x3 are both free variables. So the solution x is going to have the form x1 is negative x3, but x2 and x3 are both free. So I can write this as x2 times 0, 1, 0. So I think I don't need to fill in all the details here, right? I'm probably filling in too many details for you guys. Negative 1, 0, 1. And so the eigenspace corresponding to lambda equals 2, that eigenvalue is the span of these two basis vectors, 0, 1, 0, and negative 1, 0, 1. So this is a two-dimensional eigenspace, which is a subspace, in this case, of R3. So the individual vectors have 3 components, but they're, the span of those two is like a plane sitting in R3. So any linear combination of these two would give me an eigenvector. I could pick x2 equals 1, x3 equals negative 5. See what I get? That's an eigenvector. The only linear combination that is not an eigenvector is x2 equals 0 and x3 equals 0. So the 0 vector is never, ever, ever an eigenvector. One little thing you got to keep in mind. So that exercise is sort of the point of this section. And let's turn a page, all right? A little bit more. So a little bit more theoretical discussion here now. So why would anybody care about eigenvalues and eigenvectors? Here is an interesting theorem. Lambda equals 0 is an eigenvalue of A if and only if A is not invertible. Not invertible, okay? kind of reminds me of determinant 0, right? There's a connection there. Because a square matrix is not invertible if and only if its determinant is 0. Now we're saying a square matrix is not invertible if and only if lambda equals 0 is an eigenvalue. Okay? So here's the proof. I think we can follow this. Suppose lambda equals 0 is an eigenvalue. Then there exists a vector x different from 0, okay, such that ax equals 0x. So I put 0 in the lambda position. This is the defining equation for eigenvalue. Ax equals lambda x. You might want to write that right next to that, equals 0. And what that means is ax equals 0 has non-trivial solutions. If ax equals 0 has non-trivial solutions, A is not invertible. I feel like I want to write down what I just said in words so you see that. So what we're saying here is ax equals lambda x. That equation, if lambda equals 0 as an eigenvalue, takes this form. Ax equals a 0 vector. So we're saying x is a non-zero solution to this equation, to the homogeneous equation. That means A cannot be invertible. Or if you want to say what happened to A minus lambda I, x equals 0. This is really the same. I'm just saying the same thing in a slightly different way, just so you can see the notation. A minus 0I, that's just the 0 matrix. These are vectors. And so that's that a matrix is not invertible if and only if 0 is an eigenvalue. They don't give that one a number in the book. I don't know why. I think it should have a number, but it doesn't. So now we get to theorem 1 for chapter 5, which is the textbook's number 1. The eigenvalues of a triangular matrix are the entries on the main diagonal. And, remember, a triangular matrix has all zeros below the diagonal or all zeros above the diagonal. And we're going to look at that some more in the next section. It's real easy to show why that's true in 5.2. We're going to wait and show that's true in 5.2. And the book brings it up now because they want us to think about theorem 2. If V1 through VR are eigenvectors corresponding to distinct eigenvalues, lambda 1 to lambda r. So V1 through VR, this is a list of, we're up here, non-zero vectors. And lambda 1 through lambda r, those are just scalars. So those are distinct eigenvalues. I mean, these are different scalars. One of them could be 0, one of them could be 5, one of them could be -6. Then those vectors, V1 through VR, must be linearly independent. Okay? And I'm just going to say a little bit here about this argument, because I think this is something you're going to, no, I think I'm going to leave it for you guys to do on your own, because it gets a little bit involved showing why eigenvectors that correspond to distinct eigenvalues have to be linearly independent. I'm just going to leave that as a fact for us. But the proof is written out in detail here on the handout for you to read, and it extends onto the next page and goes on and on and on and on and on. So I think that's all we're going to say about that section. And I'm going to give you a 5.2 handout. So let's start a little bit of 5.2 for a few minutes. So the characteristic equation, it's up there on the screen as you wait to get your piece of paper. Oh, that's for John. Yeah. Okay, so I guess we just mentioned this a moment ago. Recall that a square n by n matrix is non-invertible if and only if its determinant is equal to 0, right? That's a fact we know pretty well. So let A be an n by n matrix with eigenvalue lambda. Then there's a vector x not equal to 0 such that A minus lambda I times x equals 0. That's what we've just been talking about. Okay. So the above equation has a non-trivial solution, which means A minus lambda I is non-invertible, right? That was, all right, slow down. So on the previous handout, we talked about how a relationship between A being non-invertible and the eigenvalue having an eigenvalue having value 0. This is a very different kind of statement here. We're saying that because if lambda is an eigenvalue, this equation has a non-trivial solution for x, then the matrix A minus lambda I has to be non-invertible. And so the determinant of A minus lambda I has to be 0. And conversely, if the determinant of A minus lambda I is 0, A minus lambda I is non-invertible. So A minus lambda I x equals 0 has to have a non-trivial solution. And that means that lambda is an eigenvalue. So this is going to be one of our most useful facts that we're going to use and that you're going to have to apply on our next exam probably. A scalar lambda is an eigenvalue of a square matrix A if and only if the determinant of A minus lambda I is 0. Okay? And I don't want to work all the way through that, but let's set it up and then we'll quit for today. Let me just, this is actually going to be the theorem that we apply to find eigenvalues for a matrix. And that's why in the exercise I'm saying find the eigenvalues of A equals 1821. And just before we go into that, sometimes we've started with an eigenvector and found a corresponding eigenvalue. Sometimes you start with an eigenvalue, find a corresponding eigenvector. From now on, we're almost always going to find the eigenvalues first for a matrix, and then find the corresponding eigenvectors or eigenspaces, really, that correspond to. And 2 minutes. Let's write this down. So what is A minus lambda I is 1821 minus lambda times the identity matrix 1001. So this would generalize to 3 by 3 or larger dimension. So I'm writing lambda because I don't know what the eigenvalues are yet here, right? I'm going to try to find them. I have 1821 minus lambda 0, 0, lambda, right? And so I end up with 1 minus lambda in the first position, then 8 minus 0 or 8, 2 minus 0 or 2, 1 minus lambda in that fourth position. We're pretty quickly, we're going to get very comfortable going right to this form of the matrix. We're going to notice that we have these minus lambdas being subtracted on the main diagonal. What we're going to want to do is compute the determinant of a minus lambda I, which is the determinant of that thing, 1 minus lambda 8 to 1 minus lambda. Okay. Now that's a 2 by 2. It should be pretty easy for you to find the determinant. And guess what we're going to do with that determinant? It's not a number, right? It's going to have a variable in it. We're going to set it equal to 0 and solve next time. So I'm just going to say to be continued, because we're out of time. And we're already overlapping into Wednesday a little bit. So it's getting exciting now. Okay, that's it.